The universe operates clocks more precise than anything humans have built. They beat with mathematical perfection that makes our best timepieces look primitive. You might assume accurate timekeeping requires controlled laboratory conditions. That assumption is completely wrong. Tonight we're discovering how the most violent deaths in space create the most perfect clocks, and why these stellar corpses keep better time than anything on Earth. Before we begin this cosmic mystery, drop a comment about where you're listening from. If these stellar discoveries fascinate you, consider subscribing. These explorations of deep space are meant to be shared. In 1967, a Cambridge student noticed something that shouldn't exist. Radio waves arrived from deep space, every 1.337 seconds. Exactly. Jocelyn Bell stared at data that defied explanation. Natural objects don't keep perfect rhythm. Stars flicker, planets wobble. Nothing in space maintains clockwork precision. Each signal lasted mere milliseconds. Between signals, complete silence. Then another perfect beat. Week after week, no variation whatsoever. Bell's team suspected alien technology. They nicknamed the source Little Green Men 1. The regularity seemed so artificial that extraterrestrial signals became their best guess. Nothing natural could maintain such mechanical perfection. They'd stumbled upon the universe's most accurate timepieces. These weren't alien broadcasts. They were the remnants of stellar explosions, transformed into cosmic metronomes that would revolutionize our understanding of time itself. These spaceborne clocks achieve precision that humbles human engineering. The most advanced atomic clocks on Earth drift by 1 second every 300 million years. Some of these cosmic timepieces perform thousands of times better. The fastest ones spin hundreds of times per second. They're called millisecond pulsars because they complete full rotations in thousandths of a second. Their timing stability surpasses anything scientists have built in laboratories. This level of accuracy defies comprehension. If one started ticking when the universe began, it would be off by less than 1 second today. No human technology approaches this performance. These objects maintain their precision through physics beyond earthly experience. They operate under gravitational forces millions of times stronger than anything we encounter. Extreme stellar death creates clockwork that makes our finest chronometers look like crude sundials. The signals seemed too perfect to be natural. Radio telescopes detected pulses arriving with mechanical regularity from multiple locations across space. Scientists faced an unprecedented puzzle that challenged their assumptions about cosmic phenomena. The Discovery team seriously considered extraterrestrial intelligence. Multiple sources broadcasting at different radio frequencies suggested coordinated alien communication networks. Each source maintained its own precise rhythm, like a cosmic telegraph system. Additional discoveries multiplied the mystery. More pulsing sources emerged across different regions of sky. Each maintained perfect timing but with different intervals. The pattern suggested technological origin rather than natural processes. The alien hypothesis collapsed when astronomers realized the truth. These weren't artificial transmissions, but natural cosmic lighthouses. Dead stars spinning at incredible speeds. Sweeping beams of radio waves across space like celestial searchlights. The universe had been operating its own communication network for billions of years. Not built by aliens, but forged in the violent death throes of massive stars. Some of these cosmic objects rotate at mind-bending speeds. The fastest ones complete over 700 rotations every second. That's faster than any mechanical device humans have ever built. These ultra-rapid rotators are called millisecond pulsars. They're stellar remnants compressed to city size but containing more mass than our Sun. Their surfaces race through space at significant fractions of light speed. At such rotation rates, the surface approaches the breaking point. Any faster and centrifugal forces would tear the object apart. These represent the universe's speed limit for spinning solid objects. They've reached the edge of what physics allows. The forces involved stagger imagination. A sugar cube-sized piece of this material would weigh as much as a mountain on Earth. Yet the entire object spins like a cosmic top, maintaining perfect balance through gravitational forces beyond human experience. These millisecond monsters demonstrate that the universe operates machinery more extreme than anything terrestrial physics encounters. The source of these cosmic clocks defied astronomers' expectations. The signals originated from objects smaller than cities but more massive than stars. These represent matter compressed to densities that Earth-based physics can barely describe. Scientists call them neutron stars. They're the compressed cores of giant stars that exploded in cosmic catastrophes called supernovas. When a massive star dies, its core collapses under its own gravity with incredible violence. The collapse creates densities beyond normal comprehension. Protons and electrons get crushed together, forming neutrons. An entire star's core gets compressed into a sphere roughly the size of a city. A teaspoon would weigh as much as a mountain. These objects spin rapidly because of physics called conservation of angular momentum. Just as ice skaters spin faster when they pull their arms inward, collapsing stars speed up dramatically during their final moments. Neutron stars represent the universe's most extreme physics laboratories. They demonstrate conditions impossible to recreate on Earth, where matter behaves according to rules that push the boundaries of known science. These neutron stars operate like cosmic lighthouses. They emit intense beams of radio waves from their magnetic poles. As the star spins, these beams sweep across space in regular patterns. The lighthouse analogy explains the pulsing perfectly. Just as a lighthouse appears to flash on and off as its beam rotates, these neutron stars seem to pulse as their radio beams sweep past Earth. We only detect signals when the beam points directly at us. Each neutron star has a unique fingerprint. The timing between pulses reveals the star's rotation period. Some pulse every few seconds, others pulse hundreds of times per second. Each maintains its own precise rhythm. The beams originate from the star's magnetic poles. These typically don't align with the rotation axis, creating the sweeping lighthouse effect. If the beam never points toward Earth, we'd never detect the neutron star at all. This cosmic lighthouse mechanism solved the mystery of the regular radio signals. Nature had created the universe's most precise timing systems through stellar death and magnetic field dynamics. These neutron stars generate magnetic fields of incomprehensible power. Earth's magnetic field protects us from solar radiation and guides compass needles. Neutron star magnetic fields are trillions of times stronger. Such intense magnetism creates conditions impossible on Earth. The magnetic field becomes so powerful that it affects the very atoms in the surrounding space. Matter gets compressed into needle-like shapes aligned with magnetic field lines. These magnetic fields accelerate particles to incredible energies. Electrons and other charged particles race along magnetic field lines at nearly light speed. When they change direction, they emit intense radio waves that create the pulsar signals we detect. The field strength surpasses anything humans can generate artificially. Laboratory magnets powerful enough to levitate frogs pale in comparison to neutron star magnetism. These objects concentrate magnetic energy on scales that dwarf planetary systems. Such extreme magnetism demonstrates how neutron stars push physics into realms far beyond earthly experience. They operate natural particle accelerators more powerful than anything human technology can achieve. These cosmic timepieces are forged in the universe's most violent explosions. When massive stars exhaust their nuclear fuel, they die in spectacular catastrophes called supernovas. These explosions briefly outshine entire galaxies. The explosion represents a cosmic conflict between gravity and nuclear physics. For millions of years, nuclear fusion in the star's core generates enough pressure to balance gravitational collapse. When the fuel runs out, gravity wins catastrophically. The core collapses in less than a second. Material falling inward rebounds off the incredibly dense core and explodes outward. This creates a shock wave that tears through the star's outer layers at thousands of miles per second. Most of the star gets blown into space, enriching the galaxy with heavy elements forged in stellar cores. The remaining core becomes a neutron star, spinning rapidly from the conservation of the original star's rotation during collapse. These supernova explosions mark the violent birth of cosmic chronometers. From stellar death emerges the universe's most precise timing mechanisms, spinning in space as monuments to gravitational extremes. Neutron stars represent the endpoint of stellar evolution for the universe's heavyweight champions. Only stars at least 8 times more massive than our Sun can create these exotic objects through their death throes. Smaller stars, like our Sun, will end their lives more peacefully. They'll expand into red giants, then fade away as white dwarf stars. But massive stars face a more dramatic fate that transforms them into neutron stars or black holes. The mass determines the final outcome. Stars between roughly 8 and 25 times solar mass become neutron stars. Even more massive stars collapse completely into black holes where not even light can escape. This creates a cosmic hierarchy of stellar death. Average stars fade quietly. Massive stars explode violently and leave behind neutron stars. The most massive stars disappear entirely behind black hole event horizons. Neutron stars occupy a special place in this hierarchy. They represent the most extreme form of matter that we can still observe directly, pushing physics to its limits while remaining detectable by our instruments. These neutron stars create gravitational fields so intense they warp space-time itself. Einstein's theories predicted that massive objects would bend the fabric of space and time. Neutron stars provide natural laboratories to test these predictions. The gravitational field near a neutron star is millions of times stronger than Earth's gravity. This extreme gravitational environment creates effects impossible to study elsewhere. Time literally runs slower in the intense gravitational field. Light gets bent when passing near these objects. Radio waves from the pulsar arrive at slightly different times, depending on their path through the curved spacetime. These tiny delays confirm Einstein's predictions with incredible precision. Binary pulsars orbiting companion stars create even more extreme testing grounds. The orbital motion generates gravitational waves that ripple through spacetime at light speed. These systems lose orbital energy exactly as Einstein's theory predicts. Neutron stars have become cosmic laboratories for testing fundamental physics. They demonstrate that Einstein's seemingly abstract theories describe real effects in the most extreme environments the universe provides. These cosmic chronometers could revolutionize space navigation. Their precise timing signals reach across interstellar distances with mathematical accuracy. Future spacecraft could use pulsar signals like a cosmic GPS system. Traditional GPS satellites work only near Earth. Deep space missions lose contact with ground-based navigation systems. Pulsars provide timing signals that span the galaxy, creating navigation beacons for interstellar travel. Each pulsar maintains its unique signature. Spacecraft computers could identify individual pulsars by their timing patterns and use multiple signals to calculate precise positions in three-dimensional space. The system would work anywhere in the galaxy. The concept has already been tested. NASA has demonstrated pulsar navigation using signals detected by spacecraft in Earth orbit. Future missions could carry specialized detectors to receive these cosmic timing signals automatically. This represents the ultimate evolution of celestial navigation. Instead of using stars for approximate positioning, spacecraft would use neutron stars for precision navigation with timing accuracy that surpasses any earthly chronometer. Imagine compressing all of Manhattan into a marble. That barely hints at the densities inside neutron stars. Matter gets squeezed to nuclear density, where individual particles touch each other directly. Nuclear density means packing matter as tightly as it exists inside atomic nuclei. In normal atoms, electrons orbit far from the nucleus, leaving mostly empty space. Neutron stars eliminate all that emptiness through gravitational compression beyond imagination. At this density, a sugar cube would weigh 6 billion tons. That's roughly the mass of Mount Everest crushed into something you could hold in your hand. The material becomes so dense that normal physics breaks down completely. This represents matter compressed to its fundamental limits. Particles that normally maintain comfortable distances get forced into direct contact. The result creates a state of matter impossible to study in earthly laboratories. Nuclear density compression transforms ordinary matter into something that exists nowhere else in the universe except in neutron star cores. Why don't neutron stars compress even further? The answer lies in quantum mechanics and a principle that sets absolute limits on compression. Electrons simply refuse to occupy the same space, creating an invisible wall that gravity cannot break. This quantum rule is called the Pauli exclusion principle. It states that no two electrons can exist in identical quantum states simultaneously. As matter gets compressed, electrons eventually reach a point where further compression becomes impossible. White dwarf stars rely on this electron pressure to maintain their structure. But neutron stars form when gravity becomes so intense that it overwhelms even this quantum resistance. The gravitational force literally crushes electrons out of existence. When electron degeneracy pressure fails, catastrophic collapse begins. This marks the boundary between white dwarf formation and neutron star creation. Gravity wins this quantum battle through sheer overwhelming force. The failure of electron degeneracy pressure triggers the most extreme physics transformations the universe allows. Under crushing gravitational pressure, the fundamental particles of matter undergo forced transformation. Protons and electrons get smashed together so violently that they merge into completely different particles called neutrons. This process reverses normal radioactive decay. Usually, neutrons break apart into protons and electrons over time. But extreme pressure forces the opposite reaction. Protons capture electrons and transform into neutrons through violent collision. The transformation requires pressures beyond earthly comprehension. Laboratory conditions cannot recreate the forces needed to merge protons and electrons artificially. Only collapsing stellar cores generate sufficient compression. Each merger eliminates electrical charge from the matter. Protons carry positive charge. Electrons carry negative charge. When they combine into neutrons, the electrical properties disappear entirely. The result becomes electrically neutral matter. Reverse beta decay converts ordinary atomic matter into pure neutron material that exists nowhere else in the universe. After electrons disappear, neutrons become the last line of defense against total gravitational collapse. Like electrons, neutrons follow quantum rules that prevent them from occupying identical spaces. This creates neutron degeneracy pressure. Neutron degeneracy works similarly to electron degeneracy, but at much higher densities. As neutrons get packed closer together, quantum mechanics creates outward pressure that resists further compression. This pressure increases dramatically as density rises. The battle between gravity and neutron degeneracy determines the neutron star's final size. Gravity tries to crush everything into a single point. Neutron quantum pressure pushes outward with tremendous force. The equilibrium creates stable neutron star structure. This quantum pressure operates through purely mechanical quantum effects. It doesn't require heat or motion, even at absolute zero temperature. Neutron degeneracy would still prevent gravitational collapse through fundamental quantum resistance. Neutron degeneracy pressure represents matter's final stand against the crushing force of gravity. Scientists face a fundamental problem when studying neutron star interiors. No laboratory can recreate the extreme conditions that exist inside these objects. The physics governing matter at such densities remains largely unknown. The equation of state describes how matter behaves under different conditions of pressure, temperature, and density. For normal matter, scientists understand these relationships well, but neutron star conditions push far beyond known physics. Different theoretical models predict dramatically different neutron star properties. Some suggest pure neutron composition. Others propose exotic matter states that don't exist anywhere else. The uncertainty affects basic predictions about neutron star size and structure. Astronomical observations provide the only way to test these theoretical models. By measuring neutron star masses and radii, scientists can determine which equation of state matches reality. Each new measurement refines our understanding. The equation of state mystery represents one of the deepest unsolved problems in fundamental physics. At the most extreme densities, even neutrons might not survive intact. Theory suggests that sufficient pressure could break neutrons apart into their fundamental building blocks called quarks. Quarks normally exist only inside protons and neutrons, bound together by the strong nuclear force. Under normal conditions, quarks cannot exist as free particles. The strong force prevents their separation through enormous binding energy. But neutron star cores might generate pressures intense enough to overcome quark confinement. At these densities, quarks would break free from individual neutrons and form a soup of liberated fundamental particles. This quark matter would behave completely differently from normal matter. Instead of discrete neutrons, the core would contain a fluid of free quarks moving independently. Such matter exists nowhere else in the observable universe. Quark liberation represents the ultimate breakdown of conventional matter under gravitational extremes. Neutron stars display remarkable internal architecture that varies dramatically with depth. The surface resembles familiar solid matter, but conditions become increasingly exotic toward the center. The outer crust consists of heavy atomic nuclei arranged in crystalline lattice structures. This region behaves like an extremely dense solid material, similar to metals but millions of times denser than anything on Earth. Below the surface, the composition gradually shifts. atomic nuclei become neutron-rich and eventually dissolve entirely. Free neutrons begin to dominate the material composition as density increases with depth. At sufficient density, neutrons form a superfluid state where they flow without any friction or viscosity. This creates liquid-like behavior despite the enormous pressures involved. The neutrons move collectively in perfect fluid motion. This layered architecture creates a cosmic laboratory where different states of matter coexist at different depths within the same object. Deep inside neutron stars, protons form pairs that eliminate electrical resistance completely. This creates superconductivity under conditions far more extreme than any earthly superconductor. Superconductivity occurs when particles form special paired states called Cooper pairs. These pairs can move through matter without losing energy to resistance. Electric current flows forever without any power source needed to maintain it. In neutron stars, the extreme conditions favor Cooper pair formation among protons. The pairs create superconducting currents that generate enormous magnetic fields. These currents persist indefinitely without any energy loss. The superconducting currents help explain neutron stars' incredible magnetic field strength. Electric currents flowing without resistance can build up to tremendous intensities over millions of years. This creates magnetic fields trillions of times stronger than Earth's. Neutron star superconductivity demonstrates quantum effects operating on cosmic scales under gravitational extremes. Neutron stars cannot grow infinitely massive. Physics sets an absolute limit beyond which even neutron degeneracy pressure cannot prevent total gravitational collapse into black holes. This boundary is called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who first calculated it. The exact mass depends on the equation of state, but current estimates place it around 2 to 3 solar masses. Stars exceeding this limit face inevitable collapse into black holes. No known force can prevent gravitational collapse beyond the mass threshold. Even neutron degeneracy pressure becomes insufficient to maintain structural integrity. The mass limit creates a sharp boundary in stellar evolution. Neutron stars represent the most massive objects that can maintain stable structure. Beyond this point, gravity wins completely and creates black holes. This mass boundary separates the most extreme observable matter from regions where matter disappears behind event horizons. Neutron star interiors might host particles that exist nowhere else in the universe. The extreme conditions could create exotic matter states involving particles like hyperons and condensates. Hyperons are particles similar to protons and neutrons but containing strange quarks. Under normal conditions, hyperons decay rapidly into more stable particles. But neutron star conditions might stabilize them into permanent matter components. Condensates represent another exotic possibility. These involve particles called kaons forming collective quantum states similar to superconductivity. Such condensates would dramatically alter neutron star properties and behavior. Other theoretical exotic particles might emerge at neutron star densities. Pentaquarks, strangelets, and other unusual configurations could exist as stable matter under these unique conditions. These exotic particle states would create matter with properties completely unknown to earthly physics, making neutron stars into laboratories for studying fundamental particle interactions. Most neutron stars don't align their magnetic poles with their rotation axis. This misalignment creates the fundamental mechanism behind pulsar signals. The magnetic field acts like a tilted cosmic dipole spinning through space. A magnetic dipole works like a bar magnet with north and south poles. When this dipole rotates while tilted, it generates changing magnetic fields that radiate electromagnetic waves. The faster the rotation, the more intense the radiation becomes. This tilted rotation creates the lighthouse effect that makes pulsars detectable. As the neutron star spins, its magnetic axis sweeps through space like a wobbling top. Each time the magnetic beam points toward Earth, we receive a pulse of radio waves. The magnetic field strength determines the power of these electromagnetic signals. Neutron star magnetism exceeds Earth's magnetic field by trillions of times. This extreme field strength amplifies the radiated signals to levels detectable across interstellar distances. Tilted magnetic dipoles transform spinning neutron stars into cosmic radio transmitters that broadcast their presence throughout the galaxy. Rapid rotation creates a magnetic bubble around each neutron star that extends far beyond the star's physical surface. Scientists call this region the magnetosphere. It represents a zone where the neutron star's magnetic field controls all charged particles in the surrounding space. The magnetosphere forms when rotation speed creates effects that overcome normal particle motion. Charged particles get trapped along magnetic field lines and forced to rotate with the neutron star. This creates a rigid magnetic structure extending thousands of times farther than the star's radius. Within this magnetic bubble, normal space physics breaks down completely. Particles cannot move freely but must follow the curved paths dictated by magnetic field lines. The entire region rotates as a solid unit despite containing mostly empty space. The magnetosphere boundary marks where neutron star control ends and normal space begins. Beyond this boundary, particles escape the magnetic grip and resume independent motion. The size of this bubble depends on rotation speed and magnetic field strength. Magnetosphere formation creates the cosmic machinery needed to generate powerful radio beams from neutron star rotation. There's a distance from each neutron star where rotation becomes impossible. At this boundary, material would need to move at light speed to keep up with the star's rotation. Physics absolutely forbids matter from reaching such velocities. This boundary is called the corrotation radius. Inside this radius, magnetic fields can force particles to rotate with the neutron star. Beyond this radius, no force in the universe can maintain rigid rotation because it would require faster than light motion. The corrotation radius varies with rotation speed. Faster spinning neutron stars have smaller corrotation radii. The fastest pulsars compress this boundary close to the star's surface, creating extremely compact magnetospheres with intense field gradients. At the corrotation boundary, particles break free from magnetic control. They can no longer maintain rigid rotation and begin moving independently through space. This creates a natural limit on magnetosphere size regardless of magnetic field strength. The corrotation radius represents an absolute physical boundary where relativistic effects prevent further magnetic domination of surrounding space. Near the neutron star's magnetic poles, electric fields accelerate charged particles to incredible energies. These regions function like natural particle accelerators, more powerful than any human-built machine. The acceleration occurs because rotating magnetic fields generate strong electric fields near the magnetic poles. These electric fields can accelerate electrons and other charged particles to nearly light speed within distances smaller than a city block. Polar cap regions concentrate the most extreme electromagnetic forces around neutron stars. The combination of intense magnetic fields and rapid rotation creates electric field strengths millions of times greater than lightning bolts. Particles caught in these fields gain tremendous energy almost instantaneously. The accelerated particles move along curved magnetic field lines at relativistic speeds. As they follow these curved paths, they emit intense electromagnetic radiation. This process converts the neutron star's rotational energy into observable radio waves. Polar cap acceleration creates the high-energy particles needed to generate the intense radio beams that make pulsars detectable across the galaxy. High-energy particles create avalanches of new particles through quantum interactions with the neutron star's magnetic field. This process multiplies the number of charged particles by enormous factors, creating dense clouds of electrons and positrons. Pair production occurs when high-energy photons interact with intense magnetic fields. The photon's energy converts into matter, creating paired particles with opposite electric charges. Each interaction produces one electron and one positron from pure electromagnetic energy. These newly created particles immediately accelerate in the strong electric fields, gaining enough energy to create more pairs through additional photon interactions. The process cascades exponentially, with each generation creating multiple offspring particles. The cascade continues until the particle density becomes so high that the process becomes self-limiting. At this point, the neutron star magnetosphere contains billions of charged particles, all moving at nearly light speed along magnetic field lines. Pair production cascades transform individual high-energy particles into vast clouds of charged matter that enable coherent radio emission. Charged particles following curved magnetic field lines emit intense radiation through a process called curvature radiation. This mechanism generates the radio waves that make pulsars detectable from Earth. Curvature radiation occurs whenever charged particles change direction while moving at high speeds. The particles must follow the curved paths of magnetic field lines around the neutron star. Each directional change produces electromagnetic radiation proportional to the particle's energy and the path curvature. The radiation intensity depends on both particle speed and magnetic field strength. Neutron stars provide both extreme particle velocities and intense magnetic fields, creating optimal conditions for curvature radiation. The combination produces radio signals detectable across interstellar distances. Different magnetic field geometries create different radiation patterns. Particles following tightly curved paths near the magnetic poles produce the most intense radiation. This concentration explains why pulsar beams originate primarily from polar regions. Curvature radiation converts the organized motion of charged particles into the focused radio beams that characterize pulsar emissions. Individual particles produce weak radio signals, but pulsars generate signals millions of times more powerful than individual particle emissions would suggest. The secret lies in coherent emission, where vast numbers of particles radiate in perfect synchronization. Coherent emission occurs when particles emit radiation with identical timing and phase relationships. Instead of individual weak signals, synchronized particles create combined radiation where individual contributions add together constructively. The total power scales with the square of the particle number. This synchronization requires precise organization of charged particles within the magnetosphere. Plasma instabilities and wave interactions create conditions where particles naturally fall into synchronized motion. The neutron star's rotation provides the fundamental timing that coordinates the synchronization. Coherent emission explains how pulsars can be detected from thousands of light years away despite their small size. Without synchronization, individual particle radiation would be far too weak to observe across interstellar distances using earthly radio telescopes. Synchronized particle radiation amplifies pulsar signals to levels that make them among the most detectable radio sources in the galaxy. Pulsar radiation doesn't spread uniformly in all directions. Instead, it forms narrow beams concentrated around the magnetic poles, creating cosmic spotlights that sweep through space as the neutron star rotates. The beam pattern resembles a double cone extending from each magnetic pole. Most of the radio emission concentrates within these conal regions, while areas between the beams receive little radiation. This creates the characteristic lighthouse effect of pulsars. Beam width varies among different pulsars depending on magnetic field configuration and particle distribution. Typical beams span several degrees, creating narrow searchlight patterns that cover only small fractions of the sky at any given time. The rotation carries these beams across space in regular sweeping motions. Earth receives pulses only when a beam points directly at our location. If neither beam crosses Earth's position during rotation, the pulsar remains undetectable despite its powerful emissions. Beam pattern geometry determines which pulsars astronomers can observe and explains why we detect only a fraction of all neutron stars in the galaxy. Not all radio waves can escape from pulsar magnetospheres. The charged particle environment creates a natural frequency filter that blocks radiation below a critical threshold called the plasma frequency. Plasma frequency depends on the density of charged particles in the magnetosphere. Dense particle clouds raise the plasma frequency, blocking more low-frequency radiation. Sparse regions allow lower frequencies to propagate freely through the magnetosphere. Below the plasma frequency, radio waves cannot propagate through the charged particle medium. They get absorbed or reflected back toward the neutron star surface. Only radiation above this threshold can escape into space and reach Earth-based radio telescopes. This frequency cutoff explains why different pulsars appear bright at different radio frequencies. The plasma frequency varies among pulsars based on their magnetosphere, particle density, and magnetic field strength. Each pulsar creates its own characteristic frequency signature. Plasma frequency effects shape the observable radio spectrum of each pulsar and determine which frequencies astronomers must use for optimal detection. Pulsar radio waves carry information about magnetic field structure through their polarization properties. The orientation of electromagnetic waves reflects the magnetic field geometry they encountered during emission and propagation. Polarization describes the direction of electromagnetic wave oscillations. Linear polarization occurs when waves oscillate in fixed directions. Circular polarization happens when the oscillation direction rotates continuously. Most pulsars show complex combinations of both types. The polarization changes systematically across each pulse profile. As the radio beam sweeps past Earth, the observed polarization rotates in patterns that map the three-dimensional structure of the neutron star's magnetic field. These patterns provide detailed information about field geometry. Different regions of the magnetosphere impose different polarization signatures on the radio waves. By analyzing these signatures, astronomers can reconstruct the magnetic field structure throughout the emission region and trace how fields change with distance from the neutron star. Polarization measurements transform pulsars into cosmic laboratories for studying magnetic field behavior under conditions impossible to recreate on Earth. As pulsars age and slow down, they eventually become too weak to generate detectable radio signals. There's a critical rotation rate below which the electromagnetic processes shut down completely. Scientists call this boundary the death line. The death line exists because radio emission requires minimum rotation speeds to maintain the particle acceleration and cascade processes. Slower rotation reduces the electric fields that accelerate particles near the magnetic poles. Below a threshold speed, acceleration becomes insufficient to trigger pair production cascades. Without cascade multiplication, the particle density drops below levels needed for coherent emission. The pulsar effectively switches off as a radio source, even though the neutron star continues rotating. The object becomes electromagnetically silent despite remaining physically intact. Most pulsars cross the death line within 10 million years of formation. This explains why we observe relatively few pulsars, despite the fact that neutron stars should be common products of stellar evolution. The majority have simply aged beyond detectability. The death line represents the natural end of pulsar activity when rotation energy becomes insufficient to power the electromagnetic processes that create observable radio beams. Some pulsars exhibit mysterious behavior where their radio signals suddenly disappear for periods ranging from seconds to hours, then return just as unexpectedly. This intermittent silence, called nulling, occurs in roughly half of all known pulsars. During nulling episodes, pulsars become completely undetectable at radio frequencies. The signals don't fade gradually but switch off abruptly, as if someone flipped a cosmic power switch. The timing of these events appears random with no predictable pattern. The nulling mechanism remains poorly understood despite decades of study. The radio emission appears to shut down while other pulsar properties remain unchanged. This suggests that the basic neutron star rotation continues normally while only the radio-producing processes cease operation. Current theories propose instabilities in the magnetosphere particle distribution that temporarily disrupt the coherent emission process. Small changes in particle density or magnetic field configuration might switch the radio production on and off unpredictably. Nulling demonstrates that pulsar radio emission involves delicate physical processes that can be disrupted by mechanisms astronomers have yet to fully understand. Every spinning neutron star gradually loses energy through electromagnetic radiation. The rotating magnetic field acts like a cosmic brake, steadily draining rotational energy and converting it into radio waves that escape into space. This energy loss occurs through magnetic dipole radiation. When a magnetic dipole rotates, it creates changing electromagnetic fields that radiate energy away from the source. The faster the rotation, the more energy gets radiated into space. The process operates like a cosmic generator running in reverse. Instead of using external energy to create rotation, the neutron star converts its rotational energy into electromagnetic radiation. This creates a natural mechanism that gradually slows the spinning star. The energy drain continues relentlessly over millions of years. Unlike mechanical friction that can be eliminated, magnetic dipole radiation represents a fundamental physical process that cannot be stopped as long as the neutron star maintains both rotation and magnetic field strength. Magnetic dipole radiation transforms spinning neutron stars into slowly decaying cosmic clocks that mark the passage of time through their gradual deceleration. Pulsar timing reveals one of the most predictable processes in the universe. The time between pulses increases at measurable rates that can be tracked with extraordinary precision over decades of observation. Period increase occurs as electromagnetic radiation carries away rotational energy. Each radio pulse represents energy permanently lost from the neutron star's rotation. Over time, this energy loss accumulates into detectable changes in pulse timing. The slowdown rate varies dramatically among different pulsars. Young pulsars slow down rapidly, losing significant rotational energy within thousands of years. Older pulsars change much more gradually, with periods increasing by tiny fractions over centuries. Astronomers measure these changes by comparing pulse arrival times over many years. The most precise measurements can detect period increases as small as 1 part in a billion. This reveals the extraordinary stability of neutron star rotation, even while it gradually decreases. Period increase provides a cosmic stopwatch that measures both individual pulsar ages and the fundamental physics governing neutron star energy loss. How do astronomers determine when a neutron star formed? They use the current rotation period and its rate of change to calculate backwards in time, estimating when the pulsar began spinning at its original speed. Characteristic age assumes pulsar started rotating much faster than they do today. By measuring how quickly each pulsar is currently slowing down, scientists can estimate how long the deceleration process has been operating. The calculation involves dividing the current period by twice the rate of period change. This simple formula provides age estimates that often match other astronomical evidence for stellar formation times, confirming the basic accuracy of the method. Different pulsars show characteristic ages ranging from thousands to millions of years. The youngest pulsars often appear near supernova remnants, supporting the connection between stellar explosions and neutron star formation. Older pulsars have moved away from their birthplaces. Characteristic age calculations transform timing measurements into cosmic archaeology, revealing when massive stars died and left behind spinning neutron star remnants. Neutron star magnetic fields cannot be measured directly from Earth, but the rate of rotational slowdown reveals their invisible strength. Stronger magnetic fields create more intense electromagnetic radiation, leading to faster energy loss and quicker deceleration. The measurement technique relies on the relationship between magnetic field strength and energy loss rate. Pulsars with stronger fields radiate more energy through magnetic dipole radiation, causing them to slow down more rapidly than weakly magnetized neutron stars. By measuring the period increase rate, astronomers can calculate the magnetic field strength at the neutron star surface. This indirect method reveals field strengths, typically exceeding Earth's magnetism by factors of trillions. The technique assumes magnetic dipole radiation dominates the energy loss process. For most pulsars, this assumption appears valid based on the consistency between calculated field strengths and other observational evidence from radio emission characteristics. Magnetic field measurements through timing data transform rotational slowdown into a probe of neutron star magnetism invisible to direct detection. All pulsars face eventual extinction as their rotation slows beyond the threshold needed to generate detectable radio signals. This region of parameter space, where pulsars become electromagnetically silent, is called the Death Valley. Death Valley represents the graveyard of pulsar evolution. When rotation slows sufficiently, the electromagnetic processes that create radio beams shut down completely. The neutron star continues spinning but becomes invisible to radio telescopes. The transition into Death Valley occurs gradually over millions of years. Pulsars first become intermittent, switching on and off unpredictably. Eventually, they cease radio emission entirely while maintaining their basic neutron star structure. Most neutron stars formed throughout galactic history have already crossed into Death Valley. This explains why astronomers observe relatively few pulsars compared to the expected population of neutrons created by stellar evolution over billions of years. Death Valley marks the natural end of pulsar detectability, where ancient neutron stars continue their cosmic dance in electromagnetic silence. Occasionally, pulsars experience sudden jumps in rotation speed that interrupt their steady slowdown. These events, called glitches, cause the pulse period to decrease abruptly by tiny but measurable amounts. Glitches occur when the neutron star's interior readjusts its rotation to match the slower spinning crust. The neutron star interior contains superfluid neutrons that can rotate independently from the solid outer crust through quantum mechanical effects. During normal evolution, the crust slows down through magnetic braking while the interior superfluid maintains faster rotation. Eventually, the difference becomes too large to sustain, triggering a sudden readjustment where the interior transfers angular momentum to the crust. The glitch causes an immediate speed-up followed by gradual recovery to the normal slowdown rate. This recovery process reveals information about neutron star internal structure that cannot be obtained through any other observational method. Glitch phenomena transform pulsars into laboratories for studying the exotic physics of superfluidity operating under gravitational extremes impossible to recreate on Earth. Neutron star glitches reveal that these objects contain at least two distinct rotating components with different mechanical properties. The solid crust rotates at one speed while the interior superfluid spins independently at a different rate. Component separation arises from quantum effects operating under extreme gravitational conditions. The interior neutrons form a superfluid that can flow without friction, allowing it to maintain rotation speeds different from the electromagnetically coupled outer crust. The crust slows down continuously through magnetic braking while the superfluid interior maintains higher rotation speeds. This creates increasing rotational lag between components until the superfluid suddenly transfers angular momentum to the crust through quantum vortex interactions. After each glitch, the components gradually recouple through friction like processes operating between the superfluid and crust. This recovery phase can last months or years, providing detailed information about neutron star internal dynamics. Component separation demonstrates that neutron stars operate as complex mechanical systems with multiple independent parts interacting through exotic quantum processes. Some old neutron stars get a second lease on life when they acquire material from companion stars. This accretion process can spin up the neutron star to millisecond periods, creating recycled pulsars with renewed radio emission. Reactivation occurs in binary star systems where mass transfer from a companion star adds angular momentum to an aging neutron star. The accreted material spirals inward, transferring its orbital energy to the neutron star's rotation and gradually spinning it up. The process can continue for millions of years as material slowly streams from the companion star onto the neutron star surface. Eventually, the neutron star rotation increases enough to restart the electromagnetic processes needed for radio pulse generation. Recycled pulsars often show different characteristics from young pulsars. They typically have weaker magnetic fields and much faster rotation rates, reflecting their different evolutionary history through binary evolution rather than direct supernova formation. Reactivation creates a second population of pulsars with properties distinct from normal evolutionary sequences, extending neutron star detectability far beyond typical Death Valley timescales. Even the most stable pulsars show small, unpredictable variations in their pulse arrival times that cannot be explained by simple rotational slowdown. These random fluctuations, called timing noise, represent the fundamental limit to pulsar timing precision. Timing noise appears as irregular wandering in pulse arrival times over timescales of months to years. Unlike glitches, which create sudden discrete changes, timing noise produces continuous random variations that make long-term timing predictions impossible. The source of timing noise remains poorly understood despite decades of study. Possible causes include small-scale changes in neutron interior rotation, magnetosphere variations, or coupling fluctuations between different stellar components. Young pulsars typically show more timing noise than older ones, suggesting the phenomenon relates to internal processes that stabilize as neutron stars age. The most stable millisecond pulsars exhibit timing noise levels approaching the limits of measurement precision. Timing noise demonstrates that even the universe's most precise clocks contain fundamental unpredictability that prevents perfect long-term timing accuracy. Astronomers plot pulsar periods against their rates of change to create evolutionary maps showing how neutron stars age over time. These diagrams, called pp dot plots, reveal the pathways pulsars follow from birth to electromagnetic death. The p-dot diagram displays period on one axis and period derivative on the other axis. Each pulsar appears as a point on this plot, with its position determined by current timing measurements. Lines of constant age and magnetic field strength create a grid across the diagram. Young pulsars cluster in regions with short periods and rapid period increases. As they age, pulsars move systematically toward longer periods and slower rates of change. Eventually, they cross the death line and become undetectable. Special populations like millisecond pulsars occupy different regions of the diagram, reflecting their unique evolutionary histories through binary accretion. This creates distinct branches in pulsar evolution separated from normal single-star evolution paths. P-dot diagrams transform individual timing measurements into comprehensive maps of neutron star evolution throughout the galaxy. The relationship between rotational slowdown and current rotation rate reveals which physical processes dominate neutron star energy loss. This relationship, quantified by the breaking index, distinguishes between different theoretical models of pulsar evolution. Breaking index measures how the rate of energy loss depends on rotation speed. Pure magnetic dipole radiation predicts a specific value of 3 for this parameter. Measurements that deviate from 3 indicate additional energy loss mechanisms beyond simple electromagnetic radiation. Most measured breaking indices fall below the theoretical prediction for magnetic dipole radiation. This suggests that other processes contribute to neutron star spin-down, possibly including particle winds, gravitational wave emission, or changing magnetic field structure. The breaking index evolves as pulsars age and their energy loss mechanisms change. Young pulsars may show different breaking behavior than older pulsars as their magnetosphere properties and particle acceleration processes evolve over time. Breaking index measurements transform timing observations into tests of fundamental physics governing neutron star energy dissipation and magnetic field evolution. Most pulsars follow a predictable pattern of steady rotational slowdown over millions of years. These normal pulsars spin with periods measured in seconds and gradually decelerate as electromagnetic radiation drains their rotational energy. Normal pulsars represent the baseline of neutron star evolution. They formed directly from supernova explosions and have been steadily slowing down ever since. Their periods typically range from milliseconds to several seconds, with most clustering around 1 second rotation times. These pulsars show consistent timing behavior with occasional glitches interrupting their otherwise steady deceleration. Their radio emission remains stable over years of observation, making them reliable cosmic clocks despite their gradual slowdown. The magnetic field strengths of normal pulsars fall within a typical range of about 1 trillion times Earth's field strength. This magnetism drives their radio emission through the standard lighthouse mechanism of rotating magnetic beams sweeping across space. Normal pulsars provide the foundation for understanding neutron star physics and serve as the comparison standard for more exotic pulsar varieties. Binary evolution creates neutron stars that rotate at incredible speeds. These millisecond pulsars complete full rotations in thousandths of a second, making them the fastest rotating objects known in the universe. Millisecond pulsar formation requires a two-step process involving stellar death followed by stellar resurrection. The neutron star first forms through normal supernova explosion, then gets spun up to extreme speeds through mass transfer from a companion star over millions of years. The accretion process gradually adds angular momentum to the aging neutron star. Material spiraling inward from the companion transfers its orbital energy to neutron star rotation, eventually spinning it up to hundreds of rotations per second. These ultra-fast rotators maintain extraordinary timing stability. Their rotation periods change so slowly that they rival atomic clocks in precision. The fastest ones pulse over 700 times per second while maintaining clockwork regularity. Millisecond pulsars represent recycled neutron stars given new life through binary evolution, creating cosmic chronometers with unmatched precision and longevity. Some neutron stars possess magnetic fields thousands of times stronger than typical pulsars. These magnetars generate magnetism so intense that it affects the very structure of atoms in the surrounding space. Magnetar magnetic fields reach strengths of quadrillions of times Earth's magnetism. At such intensities, the magnetic field energy exceeds the binding energy of atomic nuclei. Matter gets compressed into needle-like shapes aligned with magnetic field lines. These extreme magnetic fields create unique observational signatures. Instead of radio waves, magnetars primarily emit X-rays and gamma rays through magnetic field interactions. Their emission often appears irregular and unpredictable compared to normal pulsar radio signals. Magnetar formation requires special conditions during neutron star birth. The exact mechanism remains unclear, but it likely involves unusual magnetic field amplification during stellar collapse or early neutron star evolution through dynamo processes. Magnetars demonstrate that neutron star magnetic fields can reach extremes far beyond normal pulsar ranges, creating objects where magnetism dominates all other physical processes. Why do some pulsars have stellar companions? Binary pulsar systems form when both stars in a binary system are massive enough to become neutron stars, or when a neutron star captures material from an evolving companion star. Binary pulsars provide unique opportunities to test Einstein's theory of general relativity. The orbital motion creates gravitational waves that carry away energy and cause the orbit to decay at precisely predictable rates according to Einstein's equations. The Hulse-Taylor binary pulsar offered the first indirect detection of gravitational waves. Measurements of its orbital decay matched Einstein's predictions exactly, providing compelling evidence for gravitational wave existence decades before direct detection became possible. Different types of binary pulsars form through various evolutionary pathways. Some contain two neutron stars, others pair neutron stars with white dwarf companions. Each configuration creates different observational properties and evolutionary timescales. Binary pulsars transform neutron stars into laboratories for testing fundamental physics, under gravitational conditions impossible to recreate artificially on Earth. Certain millisecond pulsars cannot coexist peacefully with their companion stars. These black widow pulsars emit such intense radiation that they gradually evaporate their stellar companions through destructive high-energy bombardment. The evaporation process occurs through pulsar-wind interaction with the companion star atmosphere. High-energy particles and radiation from the pulsar strip away material from the companion's outer layers, creating expanding clouds of ionized gas. Black widow systems show characteristic orbital modulation as the evaporating companion material periodically blocks the pulsar emission. These eclipses reveal the ongoing destruction process and allow astronomers to study the interaction physics. The companion stars in black widow systems are typically very low-mass objects, often brown dwarfs or degenerate stellar remnants. These weak companions cannot resist the pulsar's destructive influence and slowly lose mass over millions of years. Black widow pulsars demonstrate the violent side of binary evolution, where energetic neutron stars gradually consume their stellar partners through radiation pressure and particle bombardment. Mass transfer between neutron stars and companion stars creates complex gravitational interactions. Spider pulsars show dramatic orbital changes as material flows between the two objects, creating unpredictable variations in timing and emission properties. The material transfer process varies with orbital phase and companion star evolution. Sometimes matter flows from companion to neutron star, spinning it up. Other times, pulsar radiation pressure drives material away from the system entirely. These competing processes create complex orbital dynamics that change over timescales of years or decades. The orbital period can increase or decrease unpredictably as the mass distribution between objects shifts through ongoing material exchange. Spider pulsar emission properties also vary as the material environment around the neutron star changes. Dense accretion streams can temporarily block radio emission or alter the magnetosphere structure, creating timing irregularities. Spider pulsars showcase the complex interplay between gravity, radiation pressure, and mass transfer in close binary systems containing neutron stars. Newly formed neutron stars often appear embedded within the expanding debris clouds of their parent supernova. These young pulsars emit tremendous amounts of energy across all wavelengths from radio waves to gamma rays. Young pulsar identification relies on their association with supernova remnants and their characteristic high-energy output. They typically show rapid rotation periods and strong magnetic fields inherited from their recent formation through stellar collapse. The most famous young pulsar sits at the heart of the Crab Nebula, formed during a supernova explosion observed by Chinese astronomers in 1054 AD. This pulsar rotates 30 times per second and powers the glowing nebula through its high-energy particle output. Young pulsars lose energy rapidly through electromagnetic radiation and particle acceleration. They slow down much faster than older pulsars, with rotation periods increasing noticeably over decades of observation. Young pulsars provide direct connections between stellar death and neutron star formation, offering glimpses of neutron star properties during their first million years of existence. Not all spinning neutron stars produce detectable radio signals. Radio-quiet pulsars emit X-rays and gamma rays but remain silent at radio frequencies, suggesting different emission mechanisms operating in their magnetospheres. Radio-quiet behavior might result from unfavorable geometric alignment between magnetic and rotation axes. If the radio emission cone never sweeps across Earth's direction, These pulsars would appear radio silent despite active electromagnetic processes. Alternative explanations propose different particle acceleration mechanisms that favor high-energy photon production over radio wave generation. The magnetosphere conditions might suppress coherent radio emission while maintaining particle acceleration that creates X-ray and gamma-ray signals. Discovery of radio-quiet pulsars required space-based X-ray and gamma-ray telescopes capable of detecting their high-energy emission. Ground-based radio surveys would completely miss these objects despite their active neutron star status. Radio-quiet pulsars demonstrate that neutron star electromagnetic activity can operate through multiple pathways, not all of which produce the radio lighthouse signals traditionally associated with pulsar behavior. Some pulsars exhibit puzzling on-off behavior, where their radio emission suddenly disappears for extended periods, then returns just as unexpectedly. This intermittent switching can last from minutes to months with no predictable pattern. The switching mechanism remains poorly understood despite extensive study. During off periods, pulsars become completely undetectable at radio frequencies while presumably maintaining normal rotation and basic neutron star structure. Current theories suggest magnetosphere instabilities that temporarily disrupt the particle acceleration and coherent emission processes. Small changes in magnetic field configuration or particle density might switch radio production on and off unpredictably. Some intermittent pulsars show correlations between switching behavior and other timing properties like rotation period derivatives. This suggests the intermittency connects to fundamental neutron star evolution processes rather than random external influences. Intermittent pulsars reveal that radio emission represents a delicate process easily disrupted by mechanisms astronomers have yet to fully understand or predict. Many neutron stars move through space at velocities far exceeding typical stellar motions. These high-velocity pulsars travel at hundreds of kilometers per second, fast enough to escape the gravitational pull of their home galaxies entirely. High velocities originate from asymmetric supernova explosions that act like cosmic rocket engines. If the stellar explosion doesn't proceed symmetrically, the neutron star receives a powerful kick that accelerates it to extreme velocities. The fastest pulsars show proper motion across the sky detectable through precise position measurements over many years. Some move fast enough to create bow shock waves as they plow through interstellar gas clouds at supersonic speeds. These velocity measurements provide information about supernova explosion mechanisms and neutron star formation processes. The kick velocities suggest that stellar collapse often involves significant asymmetries that impart momentum to the resulting neutron star. High-velocity pulsars demonstrate that neutron star formation can be an explosive process that launches these cosmic bullets on trajectories that carry them throughout the galaxy and beyond. Astronomers measure the exact moment each pulsar signal reaches Earth with extraordinary precision. These arrival time measurements achieve accuracy down to billionths of a second, creating the foundation for using pulsars as cosmic clocks. The measurement process requires atomic clock synchronization and precise knowledge of telescope locations. Radio telescopes record the exact timestamp when each pulse arrives, corrected for all known delays, including signal processing time and atmospheric effects. Modern pulsar timing achieves precision that rivals the best atomic clocks on Earth. The most stable pulsars can be timed to accuracies of a few nanoseconds over observation spans of many years. This represents timing precision of 1 part in billions of billions. The arrival time data accumulates into timing data sets spanning decades for the best-studied pulsars. These long-term records reveal not only the pulsar's basic rotation, but also tiny variations caused by various physical effects acting on the neutron star. Nanosecond timing precision transforms pulsars into cosmic laboratories for testing fundamental physics through their incredibly stable rotational behavior. What happens when pulsar predictions don't match observations perfectly? Scientists analyze the small differences between expected and actual pulse arrival times to discover new physical phenomena affecting neutron star behavior. These differences, called timing residuals, typically measure microseconds or less. They represent deviations from simple rotational models that assume constant period changes. Any additional physics affecting the pulsar shows up as systematic patterns in these residuals. Timing residuals have revealed gravitational wave effects, planetary companions, and neutron star interior physics that would be impossible to detect through other methods. The residuals act like a cosmic seismograph recording tiny disturbances in space-time and stellar structure. The analysis requires sophisticated statistical techniques to distinguish real physical effects from measurement noise and systematic errors. Patterns in residuals must persist over multiple years to confirm genuine discoveries rather than instrumental artifacts. Timing residual analysis transforms tiny measurement discrepancies into probes of exotic physics operating in the most extreme gravitational environments. Radio waves from pulsars don't all arrive at Earth simultaneously. Lower frequency signals travel slightly slower through interstellar space than higher frequency ones, creating measurable delays that reveal the density of free electrons between stars. This delay occurs because radio waves interact with free electrons in interstellar space. The interaction strength depends on radio frequency, causing lower frequencies to lag behind higher frequencies by measurable amounts during their journey to Earth. Dispersion correction requires simultaneous observation at multiple radio frequencies. By measuring the delay differences across the frequency range, astronomers can calculate the total number of free electrons along the line of sight to each pulsar. The dispersion measure provides a direct probe of interstellar medium density and structure. Variations in dispersion over time reveal changes in electron density caused by interstellar weather and the motion of both Earth and pulsars through space. Dispersion correction removes frequency-dependent effects to reveal the true pulsar timing, while simultaneously providing information about the interstellar environment between stars. Earth's orbital motion around the Sun creates predictable variations in pulsar arrival times throughout the year. These variations, called Raman delays, occur because Earth's changing distance from each pulsar affects signal travel time. The delay reaches maximum values of about 8 minutes for pulsars located perpendicular to Earth's orbital plane. This represents the difference in light travel time between Earth's closest and farthest approach to the pulsar during our annual orbit. Raman delay correction requires precise knowledge of Earth's orbital position and velocity. The correction removes the apparent timing variations caused by our changing viewpoint, revealing the intrinsic pulsar timing behavior independent of Earth's motion. Historical significance connects this effect to the first measurement of light speed. Raman discovered the finite speed of light in 1676 by observing similar delays in Jupiter's moon eclipses as Earth's orbital position changed. Raman delay correction demonstrates how pulsar timing must account for solar system dynamics to achieve the precision needed for fundamental physics experiments. The Sun's gravity creates measurable delays in pulsar signals that vary with Earth's orbital position. This gravitational time delay effect, predicted by Einstein's general relativity, provides ongoing tests of relativistic physics using cosmic clockwork. Einstein delay occurs because gravity warps spacetime around massive objects like the Sun. Radio waves passing through this curved spacetime travel along paths that take longer than straight-line propagation through flat space would require. The delay varies sinusoidally with Earth's orbital position, reaching maximum values when pulsar signals pass closest to the Sun. The effect amplitude depends on both the Sun's mass and the geometry between Earth, Sun, and pulsar positions. Measurements of Einstein delay confirm general relativity predictions with remarkable precision. The observed delays match theoretical calculations to within measurement uncertainties, providing continued validation of Einstein's gravitational theory. Einstein delay correction transforms pulsar timing into ongoing experiments testing fundamental gravitational physics using natural cosmic laboratories. When pulsar signals pass close to the Sun during Earth's orbit, they experience additional delays caused by gravitational time dilation. This Shapiro delay effect provides direct measurements of how gravity slows the passage of time itself. Shapiro delay occurs because time runs slower in stronger gravitational fields. Radio waves passing near the Sun experience this gravitational time dilation, causing them to take longer to complete their journey compared to signals following paths far from massive objects. The delay is largest when Earth's Sun and pulsar align geometrically so that signals graze the Sun's edge. During these superior conjunctions, the additional delay can reach several hundred microseconds for the closest approach angles. Shapiro delay measurements provide some of the most precise tests of general relativity available. The effect depends directly on the relativistic parameter that determines how gravity couples to time, making it an ideal probe of fundamental gravitational physics. Shapiro delay detection transforms routine pulsar observations into precision tests of Einstein's most profound insights about the relationship between gravity, space, and time. Pulsars move through space relative to Earth, creating systematic changes in their apparent timing behavior. This proper motion effect allows astronomers to measure three-dimensional velocities of neutron stars located thousands of light-years away. Proper motion affects pulsar timing through Doppler effects and changing signal path lengths. As pulsars move closer to or farther from Earth, their signals become compressed or stretched in time, while changing distances alter the total travel time. The motion creates characteristic signatures in long timing data that reveal both the pulsar's velocity across the sky and its motion along the line of sight. These measurements require years or decades of observations to accumulate sufficient precision for detection. Proper motion measurements have revealed that many pulsars move at hundreds of kilometers per second, much faster than typical stellar velocities. These high speeds provide evidence for violent neutron star birth processes during supernova explosions. Proper motion detection transforms pulsar timing into a technique for measuring stellar velocities across interstellar distances with precision impossible through other astronomical methods. How do pulsar clocks compare with humanity's best timekeeping technology? Direct comparisons between pulsar timing and atomic clock networks reveal that nature produces chronometers competitive with our most sophisticated artificial timepieces. The comparison requires careful analysis of both pulsar timing stability and atomic clock performance over identical time periods. International atomic time standards provide the reference against which pulsar timing precision gets measured. The most stable millisecond pulsars achieve timing precision comparable to hydrogen maser atomic clocks over observation periods of several years. Some pulsars maintain timing stability better than 1 part in 100 billion, rivaling laboratory standards. Pulsar timing offers advantages that artificial clocks cannot match. Pulsars operate in space environments free from terrestrial disturbances, and their signals can be received simultaneously by multiple observatories worldwide for independent verification. Clock comparison studies demonstrate that cosmic evolution has produced natural timekeeping systems that challenge the best achievements of human technology and precision engineering. Multiple pulsars observed simultaneously could create an independent time standard immune to terrestrial disruptions. This pulsar time scale would combine signals from many cosmic clocks to achieve timing precision exceeding any single pulsar or atomic clock. The pulsar time scale concept involves weighted averaging of timing data from the most stable pulsars in the galaxy. Each pulsar contributes according to its timing precision, with the most stable objects receiving the highest weights in the combined time standard. Such a system would offer unique advantages over terrestrial time standards. Pulsar signals originate from space and remain unaffected by earthquakes, power failures, or other disruptions that could compromise ground-based atomic clock networks. Implementation requires international cooperation to maintain continuous monitoring of the pulsar network using radio telescopes distributed worldwide. The system would provide backup timing standards for critical infrastructure, including navigation satellites and financial networks. Pulsar time scale development represents the ultimate evolution of cosmic timekeeping, where humanity harnesses the galaxy's most precise clocks for technological applications. Some pulsars maintain extraordinary timing precision across multiple decades of observation. These long-term stability measurements reveal neutron stars as among the most predictable objects in the universe despite their exotic internal physics. Long-term stability analysis correcting for all known effects, including dispersion variations, proper motion, and relativistic delays. After removing these predictable changes, the remaining timing variations reveal the intrinsic stability of neutron star rotation. The best millisecond pulsars show timing stability over 20-year periods that exceeds the performance of early atomic clocks. This stability persists despite the extreme physics operating inside neutron stars, suggesting remarkable mechanical precision in these cosmic objects. Stability measurements provide constraints on neutron star internal structure and evolution. The observed precision limits how much the interior can change over time and reveals information about superfluid behavior in neutron star cores. Long-term pulsar stability demonstrates that nature produces mechanical systems with precision persistence that rivals or exceeds the best human engineering achievements over equivalent timescales. Even the most stable pulsars exhibit tiny random variations that prevent perfect timing precision. These noise characteristics reveal fundamental limits to pulsar timing accuracy and provide insights into neutron star interior processes. Pulsar timing noise appears as random wandering in arrival times that cannot be predicted or corrected. The noise varies among different pulsars, with younger objects typically showing larger fluctuations than older, more stable systems. Two main types characterize pulsar noise behavior. White noise represents truly random variations that average out over time. Red noise shows correlations between measurements, creating systematic drifts that limit long-term timing precision. The noise characteristics provide information about physical processes operating inside neutron stars. Timing noise might originate from superfluid interactions, magnetic field evolution, or other internal dynamics that affect rotational stability. Noise analysis transforms timing limitations into probes of neutron star physics, revealing that even the universe's most precise clocks contain fundamental unpredictability that reflects their exotic internal structure. Deep space missions lose contact with Earth-based navigation systems beyond the outer planets. X-ray pulsar navigation offers a solution by using neutron star signals to determine spacecraft position anywhere in the galaxy without relying on ground control. X-ray pulsar navigation works by detecting the high-energy pulses that neutron stars emit in addition to their radio signals. These X-ray beams carry the same precise timing information as radio pulses, but can be detected by compact instruments aboard spacecraft. The navigation system requires specialized X-ray detectors that can measure pulse arrival times with microsecond precision. Each detected pulse provides a timestamp that reveals the spacecraft's distance from that particular pulsar based on signal travel time. Current technology demonstrates successful pulsar navigation using existing space telescopes. NASA has tested the concept aboard the International Space Station, proving that spacecraft can independently determine their position using pulsar timing without any communication with Earth. X-ray pulsar navigation creates truly autonomous spacecraft that can navigate throughout the solar system and beyond using cosmic beacons that never fade or fail. Spacecraft navigation requires at least 4 pulsar signals to determine position in 3-dimensional space plus time. This triangulation method works similarly to GPS satellites, but uses neutron stars scattered throughout the galaxy as reference points. Each pulsar provides one constraint on spacecraft location based on signal travel time. The intersection of multiple timing constraints from different pulsars pinpoints the spacecraft's exact position through geometric calculation. The triangulation accuracy depends on pulsar distribution across the sky. Widely separated pulsars provide better geometric precision than clusters of nearby sources. Optimal navigation requires pulsars spread across different regions of the celestial sphere. Mathematical algorithms solve the positioning equations in real time aboard the spacecraft. The calculations determine not only current position, but also velocity by tracking position changes over time as pulse arrival times shift due to spacecraft motion. Triangulation using pulsar signals transforms neutron stars into a galaxy-wide positioning network that operates independently of any terrestrial infrastructure. GPS satellites provide navigation signals only within Earth's immediate vicinity. Beyond the Moon, spacecraft must rely on complex ground-based tracking or develop autonomous navigation capabilities using natural cosmic reference points. Autonomous pulsar navigation eliminates dependence on Earth-based systems entirely. Spacecraft can determine their position anywhere in the solar system or beyond using only the pulsar signals they detect with onboard instruments. The system works regardless of communication blackouts or equipment failures on Earth. Solar storms, antenna malfunctions, or ground station outages cannot disrupt pulsar navigation because the signals originate from cosmic sources independent of human technology. Implementation requires spacecraft to carry pulsar databases and timing algorithms that operate without external updates. The navigation system must function for years or decades using only the information stored in onboard computers when the mission launched. Autonomous pulsar navigation creates space exploration capabilities that remain functional regardless of circumstances affecting Earth-based mission control or communication networks. Traditional navigation methods fail completely in the outer solar system and interstellar space. Deep space missions to the edge of the solar system or beyond require navigation systems that work across distances where Earth becomes just another faint star. Deep space environments present unique navigation challenges that terrestrial systems cannot address. Radio signals from Earth become too weak to detect reliably. Optical navigation using star positions requires extremely precise instruments and complex calculations. Pulsar navigation provides consistent performance across interstellar distances because neutron star signals can be detected throughout the galaxy. The same pulsars visible from Earth remain detectable from spacecraft anywhere within thousands of light years of our solar system. The navigation precision actually improves with distance from Earth as measurement errors become relatively smaller compared to the vast scales involved. A navigation error that seems large near Earth becomes negligible when measured against interstellar distances. Deep space pulsar navigation enables missions to the outer solar system and eventual interstellar probes with navigation capabilities that scale naturally with cosmic distances. How do spacecraft computers turn pulsar X-ray signals into navigation solutions in real time? XNAV technology combines specialized detectors with sophisticated algorithms that identify pulsar signals and calculate position updates continuously during flight. XNAV systems require lightweight X-ray telescopes optimized for timing precision rather than imaging quality. The detectors focus on measuring when photons arrive rather than creating detailed pictures of cosmic X-ray sources. Signal processing algorithms must distinguish pulsar signals from background X-ray noise and other cosmic sources. The software identifies characteristic pulse patterns that match known pulsars from onboard databases, then extracts precise timing information. The position calculation updates continuously as new pulse data arrives from multiple pulsars. Advanced filtering techniques combine measurements from different sources to improve accuracy and detect navigation errors caused by equipment problems. XNAV technology transforms pulsar timing data into navigation solutions using onboard computing power, creating self-contained systems that operate independently of ground-based processing centers. Pulsar timing noise creates fundamental limits on navigation precision that cannot be eliminated through better instruments or longer observations. These cosmic fluctuations determine the ultimate accuracy achievable using neutron star navigation systems. The precision boundary depends on both pulsar timing stability and observation duration. Longer observation periods generally improve accuracy by averaging out random noise, but some systematic effects limit improvement regardless of measurement time. Different pulsars provide different navigation accuracies based on their individual timing properties. The most stable millisecond pulsars enable position measurements accurate to hundreds of meters. Less stable sources provide accuracy only to several kilometers. Navigation system design must balance precision requirements against observation time and computational complexity. Higher accuracy demands longer pulsar observations, consuming more power and requiring more sophisticated data processing algorithms. Understanding precision boundaries allows mission planners to select appropriate pulsars and observation strategies that meet navigation requirements while optimizing spacecraft resources and mission timelines. Navigation missions require carefully selected pulsars that provide optimal timing stability and sky coverage. The reference catalog identifies suitable neutron stars and provides the precise timing parameters needed for navigation calculations. Catalog selection prioritizes pulsars with strong signals and stable timing behavior over long observation periods. Bright X-ray sources enable shorter observation times, while timing stability ensures navigation accuracy remains consistent throughout extended missions. The catalog must include pulsars distributed across different regions of the sky to provide good geometric positioning accuracy. Optimal navigation requires reference sources separated by large angles as viewed from the spacecraft's operating region. Each catalog entry contains the pulsar's precise timing model, including rotation period, period derivatives, and other parameters needed to predict pulse arrival times. These models require regular updates based on ongoing astronomical observations. Reference catalog development creates a standardized database of cosmic navigation beacons that enables consistent pulsar navigation across multiple missions and spacecraft designs. Spacecraft computers must perform all pulsar navigation calculations independently using only onboard processing power. The systems cannot depend on ground-based computers for complex calculations or database updates during critical navigation phases. Onboard processing requires sophisticated algorithms optimized for spacecraft computer limitations. The software must identify pulsar signals, extract timing information, and solve positioning equations using minimal memory and processing power. Real-time requirements demand that navigation updates complete within strict time limits to support spacecraft guidance and control systems. Processing delays could cause navigation errors that accumulate into significant position uncertainties over time. The algorithms must operate reliably for years without software updates or external assistance. Built-in error detection and correction capabilities ensure continued operation despite cosmic radiation effects on computer hardware. Onboard processing systems transform spacecraft into autonomous navigators capable of determining their position anywhere in space using only the computational resources they carry with them. How do multiple spacecraft maintain synchronized clocks across vast distances without constant communication with Earth? Pulsar signals provide common timing references that enable precise time coordination between widely separated vehicles. Time synchronization uses the same pulsar signals detected by different spacecraft to align their onboard clocks. Since all vehicles receive identical timing pulses from the same neutron stars, they can maintain synchronization without direct communication. The synchronization accuracy depends on how precisely each spacecraft can measure pulsar arrival times. Typical systems achieve timing coordination accurate to microseconds across solar system distances, enabling coordinated operations between multiple vehicles. Synchronized timing enables formation flying missions where multiple spacecraft must maintain precise relative positions. The common time reference allows coordinated maneuvers and scientific observations that require simultaneous measurements. Pulsar time synchronization creates distributed spacecraft networks that operate with precision timing coordination across interplanetary distances without continuous ground-based coordination. Precise pulsar timing reveals gravitational effects that map the detailed structure of planetary and asteroid gravitational fields. These measurements provide orbital information more accurate than traditional tracking methods for objects throughout the solar system. Orbital determination works by detecting tiny timing variations caused by gravitational influences on spacecraft motion. As vehicles orbit planets or pass near asteroids, gravitational forces alter their velocity in ways that show up as systematic changes in pulsar arrival times. The technique can measure gravitational effects from objects too small or distant to affect conventional navigation significantly. Asteroid gravitational fields, ring system mass distributions, and planetary satellite influences all create detectable signatures in pulsar timing data. Long-term timing observations reveal orbital evolution caused by tidal forces, atmospheric drag, and other subtle effects that accumulate over months or years. These measurements provide fundamental data for understanding solar system dynamics. Pulsar orbital determination transforms navigation systems into precision instruments for mapping gravitational fields and orbital mechanics throughout the solar system. Mars missions and asteroid exploration vehicles could benefit from pulsar navigation systems that provide continuous position updates independent of Earth communication windows. These practical applications demonstrate the technology's readiness for operational deployment. Mars mission applications include precision landing site navigation and rover positioning during communication blackouts caused by planetary alignment. Pulsar navigation maintains location awareness when Earth lies behind the Sun relative to Mars. Asteroid missions require autonomous navigation capabilities for proximity operations around small bodies with weak and poorly known gravitational fields. Pulsar navigation provides reliable position references independent of asteroid proximity effects. Current mission demonstrations have validated pulsar navigation using existing space hardware. The technology requires minimal additional mass and power compared to conventional navigation systems, while providing enhanced capabilities. Mission implementation transforms pulsar navigation from experimental concept to operational capability that enhances spacecraft autonomy and reduces dependence on ground-based tracking networks. Multiple spacecraft can share pulsar observations to achieve navigation precision impossible for individual vehicles. Fleet navigation combines measurements from several spacecraft to determine relative positions with accuracy exceeding what any single vehicle could achieve alone. Fleet coordination requires spacecraft to communicate their pulsar timing measurements to create combined navigation solutions. Each vehicle contributes its observations to a common database that improves position accuracy for all participants. The shared measurements enable relative positioning accuracy much better than absolute position accuracy. While individual spacecraft positions might be uncertain by hundreds of meters, their relative positions can be determined to within meters through combined processing. Formation flying missions benefit enormously from fleet navigation capabilities that maintain precise relative positioning across large distances. Scientific missions requiring coordinated observations can maintain formation geometry without constant ground intervention. Fleet pulsar navigation creates coordinated spacecraft swarms that navigate as integrated systems using shared cosmic timing signals to maintain precise relative positions throughout extended missions. Individual telescopes cannot detect the weakest gravitational waves, but networks of precisely timed pulsars create galaxy-sized detectors capable of measuring spacetime distortions. These pulsar timing arrays use dozens of neutron stars as cosmic stars scattered across the galaxy. Pulsar timing arrays work by monitoring multiple pulsars simultaneously and looking for correlated timing changes that could indicate gravitational waves passing through our region of space. When gravitational waves compress and stretch spacetime, they alter the distances between Earth and various pulsars. The array concept transforms individual pulsar observations into a coordinated detection system. Each pulsar acts like a single element in a vast gravitational wave antenna that spans thousands of light years across the galaxy. Detection requires years of precise timing measurements from at least 20 well-behaved pulsars distributed across different parts of the sky. The timing precision must reach nanoseconds to detect the incredibly small effects that gravitational waves produce. Pulsar timing arrays create the largest scientific instruments ever built. Using the galaxy itself as a detector for gravitational phenomena that Einstein predicted but thought would be too weak to observe. Gravitational wave detectors on Earth can only sense high-frequency ripples in spacetime. Much longer wavelength gravitational waves require detection methods that can measure effects lasting years or decades rather than fractions of seconds. Nanohertz gravitational waves oscillate billions of times more slowly than the waves detected by ground-based interferometers. These ultra-low-frequency ripples originate from supermassive black hole pairs orbiting each other in the centers of distant galaxies. The wave detection process requires comparing pulsar arrival times over many years to identify systematic patterns that match gravitational wave predictions. The waves cause Earth and distant pulsars to move closer together and farther apart in regular cycles. Only pulsar timing arrays can access this frequency range because the waves take years to complete single oscillations. Ground-based detectors operate on timescales far too short to measure such slow space-time distortions. Nanohertz gravitational wave detection opens an entirely new window for observing cosmic phenomena involving the most massive black holes in the universe. What happens when millions of gravitational wave sources throughout the universe combine into a single background signal? This stochastic background creates gravitational static that affects pulsar timing in ways that can be distinguished from other timing variations. The background forms when countless supermassive black hole mergers throughout cosmic history contribute overlapping gravitational waves that reach Earth simultaneously. Individual sources cannot be resolved, but their combined effect creates detectable statistical patterns. Stochastic background detection requires sophisticated statistical analysis of timing data from multiple pulsars. The analysis looks for correlations between different pulsars that match expected signatures of random gravitational wave noise. Recent measurements suggest the first detection of this gravitational wave background using pulsar timing array data. The signals show the characteristic statistical properties predicted for background gravitational radiation from cosmic sources. Stochastic background detection reveals the universe's gravitational wave environment and provides information about supermassive black hole populations throughout cosmic history. Earth-based experiments test Einstein's theories under relatively weak gravitational conditions. Pulsar systems create natural laboratories where gravity is millions of times stronger, providing more rigorous tests of general relativity under extreme conditions. Binary pulsars offer particularly powerful tests because their orbital motion occurs in gravitational fields far stronger than anything accessible to terrestrial experiments. The neutron stars orbit each other with velocities reaching significant fractions of light speed. These systems test multiple aspects of Einstein's theory simultaneously: gravitational time dilation, orbital precession, and gravitational wave emission all contribute measurable effects that can be compared with theoretical predictions. The tests achieve precision that exceeds laboratory experiments by many orders of magnitude. Some measurements confirm Einstein's predictions to better than 1 part in a trillion, providing the most precise tests of gravitational physics available. Pulsar experiments demonstrate that Einstein's century-old theories remain accurate even under the most extreme gravitational conditions the universe provides. Does the equivalence principle work when gravitational binding energy becomes a significant fraction of an object's total mass? Neutron stars provide the ultimate test because their gravitational binding energy equals a substantial portion of their mass energy. The equivalence principle states that gravitational mass equals inertial mass for all forms of matter and energy. This includes the gravitational binding energy that holds neutron stars together against their own gravity. Neutron stars test this principle under conditions where gravitational binding energy cannot be ignored as a small correction. The binding energy contributes measurably to the total mass energy that determines both gravitational attraction and inertial resistance to acceleration. Pulsar timing measurements verify that neutron stars respond to external gravitational fields exactly as predicted by the equivalence principle. The massive gravitational binding energy behaves identically to other forms of mass energy. Equivalence principle tests using pulsars confirm Einstein's insights about mass energy equivalence under the most extreme conditions where gravitational binding energy becomes dynamically important. Laboratory experiments cannot recreate the extreme densities that exist inside neutron star cores. Pulsars mass measurements provide the only way to study nuclear matter behavior under conditions that exceed anything achievable through terrestrial physics. The equation of state describes how matter responds to different pressures and densities. For neutron star interiors, this relationship determines the maximum mass that neutron degeneracy pressure can support against gravitational collapse. Precise pulsar mass measurements constrain theoretical models of nuclear matter under extreme conditions. Different equations of state predict different maximum masses for neutron stars, allowing observations to discriminate between competing theories. Recent pulsar discoveries include neutron stars with masses exceeding twice the Sun's mass. These measurements rule out many proposed equations of state and provide crucial information about nuclear physics at densities beyond normal atomic nuclei. Nuclear matter studies using pulsars reveal fundamental properties of matter under conditions that will never be accessible to laboratory experiments or particle accelerators. Einstein's general relativity faces competition from alternative theories that modify gravity under extreme conditions. Pulsar systems provide testing grounds where these competing theories make different predictions that can be distinguished through precise observations. Alternative gravity theories propose modifications to Einstein's equations that become important at very strong gravitational fields or cosmic scales. These theories attempt to explain phenomena like dark matter and dark energy without invoking unknown forms of matter and energy. Pulsar observations test these alternatives by measuring gravitational effects with unprecedented precision. Different theories predict slightly different values for orbital decay rates, precession angles, and other measurable quantities in binary pulsar systems. Most alternative theories fail to match the precision of pulsar observations, while Einstein's relativity continues to agree with measurements within observational uncertainties. The tests become more stringent as timing precision improves over decades of observations. Alternative gravity testing using pulsars demonstrates the robustness of Einstein's theory while exploring the boundaries where new physics might emerge under extreme conditions. Can dark matter particles affect pulsar timing through interactions too weak to detect in laboratory experiments? Some dark matter theories predict that these invisible particles could create measurable effects in the precise timing of neutron star rotation. Dark matter detection through pulsars would work by identifying timing variations that correlate with Earth's motion through the dark matter distribution in our galaxy. As our planet moves through dark matter concentrations, the interactions might slightly affect pulsar signal propagation. The detection method requires extremely stable pulsars whose timing can be monitored for decades to accumulate sufficient data. The expected effects are so small that only the most precise timing measurements could reveal dark matter interactions. Current pulsar timing data sets limits on dark matter interaction strengths that complement laboratory searches. These astrophysical constraints probe dark matter properties over much longer timescales and different energy ranges than terrestrial experiments. Dark matter detection using pulsars explores interaction mechanisms that might be invisible to underground detectors, but could accumulate into observable effects over cosmic distances and timescales. Pulsar distances and timing measurements provide independent methods for studying cosmic expansion and dark energy effects. These measurements complement supernova observations and cosmic microwave background studies to create a comprehensive picture of universal evolution. Cosmological applications use pulsar timing to measure how the expansion rate of the universe has changed over time. Gravitational wave detection through pulsar arrays also provides information about cosmic distances and expansion history. The measurements help determine fundamental cosmological parameters, including the Hubble constant, dark energy density, and the geometry of space-time on cosmic scales. Pulsar observations probe these parameters through different physical processes than other cosmological measurements. Pulsar cosmology offers unique advantages because neutron stars provide stable reference points that can be monitored for decades. Long-term timing studies accumulate information about cosmic evolution that shorter duration observations cannot access. Cosmological parameter measurements using pulsars contribute to our understanding of dark energy and the ultimate fate of the universe through independent observational approaches. The Square Kilometer Array represents the most ambitious radio telescope project ever attempted. This next-generation observatory will discover thousands of new pulsars and improve timing precision by orders of magnitude compared to current capabilities. SKA construction involves building thousands of radio antennas distributed across continents to create effective collecting areas approaching 1 square kilometer. The enormous sensitivity will detect weak pulsars currently beyond the limits of existing telescopes. The increased sensitivity will enable pulsar timing arrays with hundreds of precisely monitored neutron stars instead of the dozens currently available. Larger arrays will dramatically improve gravitational wave detection capabilities and fundamental physics tests. SKA operations will begin within the next decade and continue for generations, creating datasets that span human lifetimes. The long-term monitoring will reveal pulsar behaviors and cosmic phenomena impossible to study with shorter observation programs. The SKA era will transform pulsar astronomy from a specialized field into a major tool for studying fundamental physics, gravitational waves, and cosmic evolution through unprecedented observational capabilities.